it should be Wiley Plus Chapter 31, Quiz 1, if I'm thinking correctly. Chapter 31, Quiz 1 in Wiley Plus. This is our first Chapter 31 problem. So let's just dive into it. Okay. All right. We actually have our very first RLC circuit. So a single loop circuit consists of a resistor, an inductor, and a capacitor. So let's draw that. Here's a single loop circuit. Here's my resistor, R for resistor, and then an inductor, L for inductor. And this is the schematic symbol for a solenoid. L for inductor as in solenoid, which we've studied extensively in chapter 29, RL, and then a capacitor. So it turns out this combination occurs very frequently. So to the extent that we have to get really smart about it, this basically says a single loop circuit consists of a 7.4 ohm resistor, yes, an 11.9 Henry inductor, yes, and a 3.2 microfarad capacitor. That's all we have. We don't even have a power source. We don't have a power source, but the capacitor had an initial charge. So this is it. This is a single loop circuit consisting of a 7.4 ohm resistor and an 11.9 Henry inductor and a 3.2 microfarad capacitor. So this belongs to the class of problems known as RLC. So this is a very, very large part of chapter 31. In fact, it's basically chapter 31 is RLC circuits and with some specialties. But this is a single loop circuit, RLC circuit. This capacitor has an initial charge. So this is what happens in a perfect world. We never have resistance in a perfect world. So this is what happens in a perfect world. There's no resistance. There's no cloudy days, no social unrest. It's just pure sailing, no resistance. And you have this. This is an LC circuit. And you can see it's just oscillating back and forth purely. This is what happens when there's no resistance. This is simple harmonic motion. Simple harmonic motion is something that you should have gotten a pretty healthy dose of in your prior physics class. It's a simple harmonic motion, an example of simple harmonic motion. Life is good. There's lots of reasons that we're interested in LC circuits, but in reality, there's always some resistance. So let me go from the ideal world to the real world where we actually do have some resistance. Watch what happens. I'll make this 100 ohm resistor and then hit reset again, reset. Okay. Am I resetting? Yes. Okay, so there. So things are starting out good, looks good, but look at all of a sudden now I'm fading away. So this is called damped simple harmonic motion, which again, you should have gotten a good dose of in your prior physics class. I'm just saying that just to make you aware of what to expect and what you might need to go back and brush up on. But now I'm fading away. This is damped simple harmonic motion. This is more realistic because in reality, you always have some resistance. And this pertains to filtering circuits, which you might not have any concept of what filtering circuits are. I know I didn't until I started studying them. But what you do have a concept of is power generation. So all of this stuff is part of AC. I mean, chapter 31 is alternating currents. This is all at the heart of alternating currents, which is how pretty much our modern society is run in terms of electricity. All right. So anyway, now that is addressed. This is what happens. We have an RLC circuit. And yeah, my capacitor had an initial charge of 6.2 microcoulombs. And okay. So my capacitance has a value of 3.2 microfarads. And it had an initial charge of 6.2 microcoulombs using my numbers. So Q equals 6.2 microcoulombs. Somehow, some way, this capacitor got an initial charge. So I do have some energy in this RLC circuit. All right. So now what happens? It says calculate the charge on the capacitor after 5 cycles. So if I go back to my Fallstad circuit, let me again say, here is the perfect world. Look at that. Look at that, just a pure sinusoidal shape. And this was chapter 31 spent an enormous amount of time talking about how this shape originates. Basically, it's a game of hot potato. The capacitor and inductor are throwing the energy back and forth. So when the capacitor becomes fully charged, the inductor is completely uncharged, and vice versa. And they keep throwing this energy back and forth sinusoidally. They don't just throw it back and forth willy-nilly. They throw it back and forth in a very specific way, and that very specific way is sinusoidally, as in a sine curve or a cosine curve. All right, so let me repeat again. But now our system here, in fact, maybe I'll use the same numbers. If my numbers say a 7.4 ohm resistor. So here's, using my specific numbers, this is a 7.4 ohm resistor, and my number says 11.9. That's interesting. 11.9 ohm inductor and a 3.2 microfarad capacitor. So that's good. And my initial charge on capacitor, I think, was, anyway, some number. But this is, watch what happens when I hit reset. So things are looking good. There's 1 bounce, 2 bounces, and I'm starting to fade away. So I'm starting to lose energy because of the presence of that resistor. And you can see I'm kind of losing energy relatively gradually. But this is what happens when I have a less than perfect situation. I do have some resistance. So as far as our problem is concerned, we have that same RLC circuit, and the capacitor is fully charged, and it starts to bounce back and forth sinusoidally, just like you see here. And the question is, what happens after 5 bounces? So let's count up the bounces to find out where we're looking. All right, this is bounce 0, bounce. This is bounce 0, bounce 1, 2, 3, 4, 5. So right here, this is what we're interested in for part A. This is N equals 5 bounces. This is bounce 0, 1, 2, 3, 4, 5. That's part A. How much charge is left on this capacitor after 5 bounces? And the answer should be, well, the capacitor should have the same amount of charge that it started out with. But you can see, no, you get this decay envelope. You get this exponential decay because of that resistor. That resistor is stealing some energy. All right, so in your green sheets, in the chapter 31 lecture video, which is pretty heavy, lots of derivations were reviewed. I'm going to, I guess, look at this expression. This is the expression that says, hey, here's how you find out. This expression gives you the charge on a capacitor after a certain amount of time. It specifically says that use the analogous solution for underdamped charge decay. Okay, so I'm going to write this down. I'm going to write down the charge at some time is equal, and I'm just copying that. The initial charge, Q sub m, is called charge amplitude, or the initial charge, e to the minus RT all over 2L cosine omega d times t plus phi. So just a little discussion about this expression, because this is all going to seem new and pretty deep until you get to a point where you say, okay, yeah, this is making sense now. This is called charge amplitude. Charge amplitude is the official way of saying the maximum charge. Charge amplitude. Whenever you see this term amplitude, it's referring to the maximum possible value for, in this case, charge amplitude. This is R for resistance, so that's doesn't need to be. We don't need to spend a lot of time. That's the resistance. This is the inductance, RL, inductance, resistance, inductance. This is the phase shift. Phase shift refers to how far ahead of the starting line or how far behind the starting line your system started. Phase shift. So if you're running a 100-meter dash and you start ahead of everyone else in front of the starting line, you have a phase shift. You have a phase shift relative to everyone who's standing at the starting line. This right here, this is damped angular frequency. Damped angular frequency. This refers to basically the rate of oscillation, how quickly these bounces are happening. All right, so now this entire term right here, this is my decay term. I don't need this term in a perfect world, but I need this expression, this term right here in blue, because I do have loss. I have energy loss. So this is known as this is my decay. This is my exponential decay. And you can see in this visual, and you saw in Falstad how things, we saw in Falstad how things are decaying away because the resistor is stealing energy. This term right here is my bouncy part. So this is my bouncy part. And instead of saying bouncy part, let me more officially say this is my oscillating part. Oscillating term. Okay. So there you go. This is it. This is it. I don't need this term if there's no energy loss. On the other hand, I don't need this term if there's no oscillation back and forth, if there's no bouncing back and forth. But in this case, I need both of them, because that inductor and capacitor, they're playing that game of hot potato, throwing energy back and forth. So I need both of these terms. All right, so now that we're familiar with this term, let's figure out what happens after 5 bounces. So step number one. Well, let's see. I'm going to take a look at what's going on at time equals 0. At time equals 0, I'm going to look at what's happening right here. At time equals 0, just when we start the stopwatch, the capacitor is fully charged. So at time equals 0, I have the charge at 0 is going to equal the maximum charge, the charge amplitude, E to the minus R times 0, T is equal to 0, all over 2 times the value of the inductance. And the inductance value for me is 11 point, well, I'll just leave it as L. Okay, because I know E to the 0 is just equals 1. So that term's going to go away, times cosine of omega d times 0, because again, we're looking at what's going on at time equals 0 plus the phase shift. All right, so again, what's happening at time equals 0? So here's the result. Ready? At time, well, before I just write down, here's some low-hanging fruit. This term equals 1 at an amplitude. when you think about it, you guys, this goes back to the unit circle days. Cosine, what's the maximum value cosine can ever attain? And let's just call a quick timeout to talk about the unit circle. So here's a unit circle right here. Cosine refers to what's going on along that x-axis. So if this is the x-axis right here, this is the x-axis, and this is the cosine axis. This is the y-axis, and also known as the sine axis. Sine. So cosine is basically telling you where you are along the x-axis at the maximum possible point right here. That's cosine equals 1. Here's cosine equals 0. Here's cosine equals -1. Halfway between there, this cosine value would be √2/2, and so on and so forth. All right, so the reason I'm mentioning this is because cosine can have a maximum possible value of 1. So this term can at most spit out a value of 1. When is it going to spit out a value of 1? At a maxima point. So right here, cosine equals 1. Cosine equals 1, cosine equals 1, cosine equals 1 at all of these maximum points right here. Each and every one of them, cosine equals 1, and so on and so forth. 1, on and on and on. 1, 1, okay. All right, so then you might say, well, wait a minute, Chris, it doesn't look like 1. It looks like whatever this value is here, it's greater than this value here, and this value here is greater than this value here. So you're wrong. But I'm not wrong, because the cosine part equals 1. But the fact that this value here is greater than this value here is because of this decay term right here. So it's that term that explains why I get this decay. I'm going from full value to something less than full value, but the cosine at these amplitudes is spitting out a result of 1. All right. The other low piece of low-hanging fruit is, as mentioned, is this is equal to 1. I basically have e to the 0 equals 1. So at time equals 0, this is what I get. I get Q, the charge at time equals 0, equals that maximum possible amount of charge. And you might say, did you really have to take all this time to show that I knew this right away? Of course, at time equals 0 right here, I have the maximum amount of charge. So why did you go through all this? Just for the heck of it, just for the insights, because I think it could help here. Let's talk about what happens 5 bounces later at t equals 5t. 5 bounces later, because this is how we count it. This is bounce 1, 2, 3, 4, 5. So we're basically looking at what happens 5 bounces later. So let's go ahead and see what we get now. Q, 5 bounces means 5 periods. So N equals 5 periods. Period. The description of a period is the amount of time it takes to complete one cycle. So this is 5 cycles. 5 cycles means 5 periods. So Q at 5 periods equals QM, yes, E to the minus R times 5T. So I'm going to replace, this is 5T all over 2 times L. That's my decay term, which is not equal to 1. So that's not low-hanging fruit. Here's my cosine term. The cosine term, again, handles the bouncy behavior, the oscillation behavior. Cosine omega d times time 5t plus 5. And this still remains low-hanging fruit because I am tasked with looking at what's happening at n equals 5 periods. So I'm at a maxima point. I'm at a maxima point, which means this term once again equals 1. I'm at a maximum point, which means whatever this is, whatever this argument is here, I'm saying, I don't care what that is, because whatever that is, cosine of whatever that is equal to 1, because I'm at a maximum point. Okay, so number 4. All right, so after 5 bounces, what do I have? I have Q sub M, and here's my low-hanging fruit. This is equal to 1. So after 5 bounces, I have Q sub M. I guess I got to go with numbers now. Well, hang on. E to the minus R 5T all over 2L. We better put that in parentheses. All over 2L times 1. All right, so that's good. All right. So number 5. I need to figure out, I know what Q sub M is. Q sub M, this value right here, right? This value is the maximum charge that you started off with. This is the charge you started off with. And with each successive bounce, I'm losing some of that charge. And we got to figure out, well, how much do I have at n equals 5? But I know how much I started out with. I started out with this much charge, 6.2 microcoulombs. So let's keep running with that. All right, so after 5 bounces, I have 6.2 microcoulombs, 6.2 e to the minus 6 coulombs, e to the minus r. So r is, for me, 7.4 ohms times 5t, and then, what's t? I don't know. 5t. So I'm just going to leave it as t, all over 2 times L, 2 times L, and for me, L is 11.9 henries, 11.9 henries. There. Okay, so things were going pretty good, except what do I put for T? So let me pull up some different notes here. Okay, so I guess we're going to go to we're going to talk about the damping term. All right. This is where we recycle this expression. This expression right here is saying, if you have some damping, this is the expression you use. So just a couple of comments about this expression. You pronounce it the following. You said this is not W, this is omega. So that W is not a W, it's Greek letter omega, and it refers to damped angular frequency. So this term, well, first of all, that's Greek letter omega, which is good to know. And this is damped angular frequency, as it says here. Damped angular frequency. If I didn't have any damping, this whole term would go away. But so you can see where the correction comes in. So I'm going to use this expression to figure out that T value. So let me make some room right here, I guess. All right. Number 6. Okay, so number 6. Well, I know in general, I know omega always equals 2 pi f equals 2 pi over t. So this expression right here came from birth of a radian. It came from birth of a radian. I can't remember. I don't know if we've used it thus far. I think we have. I think we might have referenced it a bit in this course. You should have utilized this a ton in your prior physics course. But this is, again, brought to you by birth of a radian. And just because we're doing okay on time, theta is defined as S over R, which means S can be stated as R theta. If I divide both sides by time, I get V equals R omega. I know V can be expressed as distance over time. Distance for a circle is 2 pi R over T equals R omega. And then this is how you get omega equals 2 pi over T. And I remember T and frequency are inverses of each other. So anyway, I just wanted to take that 20 seconds to go through that again, birth of a radian, just because I want to avoid, I'm doing it a bit in this, but I want to avoid saying, hey, here's a magical equation. Go ahead and plug numbers into this magical equation. And we don't know where this equation came from, but if you plug numbers in, again, as if by magic, you're going to get the right answer. I always want to avoid that as much as possible because it's not the strongest approach to take. But we have to take it every now and then because this right here, this is brought to you by differential calculus, and this is brought to you by differential calculus. Some of you might have had differential calculus. Most of you have not, or at least I assume that most of you have not. All right, so here we go. I have omega equals 2 pi over t. And I also have the personalized version of omega, which says omega equals 1 over LC minus R over 2L squared. Okay, so I'm tapping into this expression. This expression right here is basically derived from this expression right here. And there's where I'm going to get a value for t. So number 8, t equals 2 pi all over the square root of 1 over LC. And for me, L is, once again, 11.9 henries. That's L. C for me is 24. No, C for me is 3.2 microfarads, 3.2 e to the minus 6 farads. Okay, so that's 1 over LC minus, it's getting kind of extended, minus R, 7.4 ohms, all over 2 times L, and L is, again, 11.9 for me, 11.9 henries, and this whole term here needs to be squared. So job number 1 is let's get a value for t and put it in calculator memory location A. And then we can go back to step 5 and get the answer. I get some number. I'll definitely double check. I got this right. I got the same answer twice. So as mentioned, and this might take, I don't know, if you're like me, sometimes you have to do the calculation 2 or 3 times or a bunch of times to get the same answer consistently. But when you do, when you get a value for t represents the amount of time it takes to complete one cycle. So now that you know how long it takes to complete one cycle, use this value, use this t in equation number 5. And then and that will give you Q. After 5 bounces, after 5 cycles, you're going to know how much charge is on that capacitor. So let's do that. Okay. I started off with 6.2, and now 5 bounces later, I'm at 5.837 microcoulombs. Okay. So I know some of you are ahead of me because I know some of you do stuff faster than I do. Some of you might be behind me, but this is us figuring out what's going on after 5 periods. And then for B, same thing for 10, and C, same thing for 100. So let's see. For B, for part B, what changes? Part B, you're just going to change. You're going to change. You're going to go, instead of 5T, it will be 10T. So we should have even less charge after 10 bounces. And then, so when I change 5T from 5T to 10T, I think everything remains identical except for this number right here. So parts B and C should go super quickly. Everything is going, it's going to be a redo, except you're going to change that from 5 bounces to 10 bounces and then 100 bounces for part C. And what we want to see is how, every bounce takes away some energy. With every bounce, we lose some energy. So I'll leave it at that and give you some time. Okay. Check in to see how everyone's doing. Okay. So Chris, Matt, Dan, Luke are good to go. Others need more time. If you don't have the answer yet to part A, definitely speak up and ask for an assist. If you just need more time, that's fine. Well, we seem to be kind of at a state of equilibrium. Again, we have Chris, Matt, Dan, Luke done. Everyone else is not done, which means you're either stuck or you just need more time. And what I'll do is I'll do the soccer match approach. I'll add some stoppage time at the end of this because nobody will run out of time. But let's move on to quiz 2. And then for those of you who just need, if you need help, you're just gonna have to speak up. I mean, as uncomfortable as that might be, you actually might have to talk. Or if you just need more time, I'll give you more time again on the backside, just because we need to start quiz 2. Let me check on chapter 31, quiz 2. This should be available. I'm just going to double check. All right. Here we go. Now, here's what I would recommend. Everyone jump into quiz 2. Because I know those, if you're like me, sometimes you just have to spend an enormous amount of time on the calculator part. Okay, quiz 2. Similar problem here. Maybe we'll get into the swing of things. We once again have an RLC circuit. RLC circuits are at the heart of modern society as far as electrical energy generation and transmission and consumption. And we're always driving by power stations too. So now we know what they're doing. We have yet again another R. So resistance, R for resistance, L for inductance, and C for capacitance. And once again, we don't have any power source. There's no battery or AC power source. It's just a resistor, an inductor, a capacitor. And we know the values on these elements. Find the time required for the maximum energy present in the capacitor during an oscillation to fall to half of its initial value. So apparently, this is just like the last problem. This capacitor starts out with some charge, starts out with some energy, starts out with some energy. And just to backtrack a bit, the energy of a capacitor lives within the capacitor's electric field. So you remember we had parallel plate capacitor, and we had these electric field lines pointing from the more positive plate to the less positive plate. And we like parallel plate capacitors because we get this very predictable electric field between those plates. And if that field is predictable, we can manipulate it. We can make it behave in certain ways. And this electric field, as mentioned, this is where the energy lives in the capacitor, as opposed to an inductor. In an inductor, the energy lives in the magnetic field, but our capacitor starts off with some energy. And in a perfect world, we don't have any resistive losses. This is what a perfect world looks like right here. This is an LC circuit. So you can see just perfectly sinusoidal reaction, sinusoidal behavior, simple harmonic motion. It's a sine wave that never diminishes. It's forever young. But then what happens is soon in the real world, there's always some losses, because wires always have some resistance in them. So that's why we always kind of have to include that resistor, not because we want to, and really not because it's really needed, but because it's just something we can't avoid. So this is what happens when you add a resistor. Look, in this case, it just faded away really quickly. What if I maybe didn't get quite so intense with that resistance? And so this is an RLC circuit. It's bouncing back and forth. It's oscillating. This is the alternating current that you always hear about whenever you see the term AC. AC stands for alternating current. DC stands for direct current. So if we go back to the problem, after how long? This says, find the time required for the maximum energy present in the capacitor during an oscillation to fall to half of its initial value. Okay, so once again, we have this term actually is familiar, and I'm saying that. Let me rephrase. This term was introduced in chapter 25. So I'm not sure if it's familiar. The only thing I will say is we've seen this before. This was a chapter 25 piece of content, and this is referring to the electrostatic potential energy that lives right here, that lives between the plates of a parallel plate capacitor. This is the electrostatic potential energy equals Q squared over 2C. And what we did with this chapter 25 expression, which was derived, we said, okay, well, I'm going to square Q. So if it's Q squared, I'm going to take this expression and square it. So if I squared this nasty looking term and then I divide by 2C, well, here I'm doing that right here. I am squaring, wait for it. I'm squaring this term. So here's me doing the heavy lifting. I'm squaring this term, dividing by 2C, and this is what I end up with. All right, so let me rewrite that, and let's use that as a starting point. Number one. All right, the electrostatic potential energy of a capacitor. In this circuit, in an RLC circuit, because now I have this alternating current behavior. Things are going back and forth sinusoidally. And on top of that, I have some losses. So I'm just going to write down QM. That's my maximum charge all over 2C. And here comes my decay term, E to the minus RT over L. And here comes the bouncing part, cos squared omega D times T plus phi. So let me just reinforce this for the nth time. This is my bouncing part. This is my decay term right here. And basically, well, this is my initial charge. So this is charge amplitude. And when I say charge amplitude, that's another way of saying this is the maximum amount of charge that you started off with right there. So those terms are still here. And because I'm squaring this cos term, notice I'm always above the y equals 0 axis. So that's what you get when you square things. All right, so we've seen this kind of we've seen this kind of situation before with RC circuits, and we're seeing it again. So here goes. All right. How much time is needed for this to fall to half of its value? So my electrostatic potential energy at time equals 0. So let's look at what happens right here. Let's happen right out of the starting gates, right at the very beginning of our analysis. We're starting off at time equals 0. This is T equals 0. Let's take a look at what's going on right there, because that's our starting point. So that's going to equal QM squared over 2C. And here comes my decay term, e to the minus RT, and T is 0 all over L. And here comes my cosine part, cosine squared omega d T plus phi. So this is actually going to go quite quickly. This low-hanging fruit, this is my decay term, and it equals 1, because E, this is E to a power of 0. E to the 0, E to the 0th equals 1. All right, so this equals 1. Once again, this can at most be 1. This equals 1 at an amplitude. And that goes back to our wonderful conversation about the unit circle. Cosine can at most be 1. 1 squared is 1. All right, so at time equals 0, I have this much electrostatic potential energy equals QM squared over 2C. Okay, number 4. At half value, at UE equals, maybe I better say UE, maybe UE, what's a good number? New, UE half. UE half. At UE equals half the value, it equals UE over 2. So I'm going to get at some time later, let's just say for the sake of conversation right here, at this point, at some T value, at T equals $, at T equal $, that electrostatic potential energy at that $sign point is equal basically to half of what I started off with, UE over 2. And I'm calling this, I guess, half. Okay. All right. So let's go with that. Number 5. UE at some time, that's my $, is going to equal QM squared all over 2C E to the minus RT over L. So T is not equal to 0. It's not equal to 0. It's equal to some value. So I don't know what that some value is. So it's just going to stay T times my bouncy part, my sinusoidal term, my oscillation term. Okay. Once again, there will be a time where this isn't going to equal 1, but for now, it always seems to be equal to 1. But don't count on that always being the case. But it is the case here because we are looking at amplitude points. Okay. All right. So here goes number 6. Well, what's a good way to do this? I'm going to say this potential energy at some time divided by the potential energy at time equals 0 equals 1/2. So does this making sense? I'm saying, here's what I'm saying. At this time, whatever this time is, again, I don't know. This is just for conversational purposes. At some time, I have this amount of electrostatic potential energy. And that's exactly half of what I had here. So whatever this value is here, it's twice this value here. So if I take this value divided by what I started off with, that equals 1/2. So I know that equals 1/2. So 1/2 is going to equal this, QM squared over 2C e to the minus RT over L, because this again went away. That's my numerator. Here's my denominator. What was my electrostatic potential energy at time equals 0? QM squared over 2C right here. So this term right here, my denominator here, this is, just to be clear, this was my electrostatic, this is what I started off with, my electrostatic potential energy at time equals 0, which I figured out here in step 3. So I'm just plugging in that result right here into my denominator. Yes, this is what's going on at some time later, and that came from here, right up above, because this whole term equals 1. All right, so there. Number 7 is, I think that's the hardest part, because now number 7, I have 1/2 equals, and then let's do some cancellation. What cancels? 1/2 QM squared cancels with QM squared. 2C here cancels with 2C there. So I have 1/2. I'm left with E to the minus RT over L. Okay, and we've seen something that's very similar to this in RC circuits, chapter 27. Take the log of both sides. Both sides. Natural log of 1/2 equals minus RT over L. Number 9, solve for T. And let's be done with it. Okay. Time check. 8:54. I'll come back to this. That's pretty involved. All right, so let's do this. See you at 9:03 a.m. Just because I know some people are still catching up with the previous problem. I don't want to go too far afield. So I will return at 9:03 a.m., which hopefully then gives you time to hammer away on wherever you need some more time. Let's move on to Wiley Plus Chapter 31, Quiz 3. Chapter 31, Quiz 3. Okay. Yet another RLC circuit, but here's something that's different. This is a driven or a powered RLC circuit. So this is really your electrical power grid, among other applications. I'm kind of like maybe really obsessing over that, because to me it's the most interesting application. This is definitely part of what's going on with electrical power generation in our world as we experience it. So let me make sure I'm sharing what I think I'm sharing. Okay, so chapter 31, quiz 3. All right, once again, an RLC circuit. Let's just go through each one. Here's R, here's L, there's C. So we've seen RLC before. And now, though, this is what's new with this problem. Now we actually have a power supply. So you know what this is? This is DTE energy. This is, I don't know how much you, how many electrical bills you pay, but DTE, Detroit Edison, is one example of an energy provider. This is from DT Energy or maybe Consumers Power or wherever you happen to get your energy from. So this comes from large electrical generators, very, very large power plants that tap into fossil fuel based heat or renewable versions of heat. But at the end of the day, this is the power plant that you write your checks to. And then when they transmit this energy, they have to deal with resistance because wires have a lot of resistance. And it turns out we deal with inductance and capacitance as well. We deal with inductance because this is basically one giant inductor, this generator. And this is where this problem comes in. So let me do the read through on the problem. We have an AC generator that's producing a peak value. This is, so just to use the vocabulary, E sub M, this is the EMF amplitude. The EMF amplitude, or for short, script E subscript M, equals 221 volts, peak value. Okay, so we have a power. We have a power generator, an AC, an alternating current power generator that, and you guys experienced this in class when you made the world's simplest generator, you were creating alternating current. It might not have been like perfect, but the fact that you were shaking those magnets back and forth and getting that little light to illuminate, that was you basically creating alternating current. All right, so this alternating current has a frequency. So we know the peak value of this source of voltage. We know that it has a frequency, F, and here's our RLC circuit. Find the capacitive reactance. All right, so here, number one. So here's a lot of, this problem will be a ton of new introductions, unless you watch the Green Sheet YouTube. If you watch the YouTube Green Sheet lecture video, then you've seen this stuff before. Part A says, what is the capacitive reactance? So ready. X sub C equals 1 over omega D times C. That's the answer. All right, so before we just go on, this is basically a little sidebar conversation about what this really is. X sub C is the capacitor's, it's the capacitor's version of resistance in an AC circuit. Okay, so we know about R. R stands for resistance. R is very familiar to us. The R refers to basically a wires or the resistance to charges flowing, resistance to charge flow. So we for sure have been introduced to R, the resistance of a wire. Now here's something new. This is called capacitive reactance. X subscript C is basically just a capacitor's resistance. Now this is not a physical. This is not a physical resistance. Maybe I'll just say not physical. This is not physical. So don't let yourself think, well, yeah, capacitor has resistance because maybe there's metal wires in place. That's not the source of this resistance. The source of this resistance is basically in this formula right here. All right, and here's an outstanding one paragraph description. Maybe I'll paraphrase it. So ready, brace yourself. A capacitor does not allow flow of direct current through it as the resistance across the gap is infinite. So that's saying, let's remember what a capacitor is. Here's a capacitor. Charge does not flow through. You never have charge flowing through a capacitor. What you do have, if you have charges flowing onto that positive plate and off of this negative plate. So the reason why a capacitor has a certain amount of resistance and an alternating current, because it takes time. It takes time for charges to build up here, and it takes time for charges to disappear from here. So that takes time. And then on top of that, if you're basically ramming current this way, and then you're reversing it, and because it's alternating current, so it's going this way one moment, and then the next moment it's going back here, that's where you get your reactance. That's where you get sort of your impedance or your resistance to flow. It's not physical. It's because you have to wait for charges to build up, and then you have to wait for them to reverse themselves and then build up in the opposite direction. So that's what's in this paragraph. This paragraph says, hey, the faster, it says, thus a capacitor will pass more current through it if the voltage is changing at a faster rate. So if you want to cause a whole bunch of charges to build up on this positive plate rapidly, then you'll increase this frequency. So if I basically say, okay, well, maybe once a minute, I'm going to deposit some charge there. And that's going to take a certain amount of time. What if I say, instead of once a minute, what if I deposit charge like once a second or once every millisecond? That is going to be that's going to be a lot more efficient. That's going to be less reactance. So anyway, there more about that because this is brand new. All right, we have another brand new term here coming up called XL. So number 2, in terms of introductions, X subscript L equals omega D times L. And this has a special name. Let me name them right here. This is capacitive reactance. This is a capacitor's version of resistance, capacitive reactance. Here's the inductor's version of resistance. This is inductive reactance. This is also not physical. This is electromagnetic reactance. Okay, not physical, not physical. This is not a physical resistance. It's basically electromagnetic. Maybe I'll just do it like that. So keep that in mind. And there's a mnemonic for here. Capacitive reactance is in the cellar. So in the cellar means you put the C, things are living down here in the cellar. So that's a mnemonic. That's in your green sheets. All right, so we have 3 kinds of resistance to current flow. We have the physical resistance of the wires. All right, so we have wire resistance, which is physical. We have capacitive reactance, which is electrical. And we have inductor reactance, which is electromagnetic. And remember what an inductor is. An inductor has inertia. So inductors, whatever an inductor is doing, it doesn't want to be bothered. If no charge is flowing through an inductor, the inductor will resist any attempt to flow charge through it. Similarly, if 5 amperes of charge is flowing through an inductor and you try to decrease that or increase it, the inductor says, I want to stay at 5 amps. So that's the inductive inertia. Anyway, there it is. Here are the 3 types of resistances we have to deal with now. So it's a more complicated world. Capacitive reactance, which is the capacitor's version of resistance, inductive reactance, which is the inductor's version of resistance, and resistance. And there's yet another brand new introduction, the Z. Z is called impedance. Impedance. Except I misspelled that. Impedance. All right, so here's this would be sort of, I think, a logical next question. If I have resistance due to my capacitor in an AC circuit, and I have resistance due to an inductor in an AC circuit, and I have a resistance due to a wire or resistors, what's the total effect of all of that? And it's given by this expression, Z equals the square root of R squared plus XL minus XC squared. So that's the other huge introduction. This is impedance. This is the net result of resistances from the capacitor, from the inductor, and from the resistor. And what I'm going to do now is probably, before I forget, let me go back. Let's talk about when the homework is due. So I just wanted to mention this in case you haven't seen it. The chapter 31 homework is due on December 12th. So that's a lot of time, which is good. So we can actually digest this pretty thoroughly, which is good because this is pretty heavy stuff. Chapter 31 is probably the heaviest lift in Physics 212. Although typically, if you survive to this point, you're kind of good with any chapter because you've gotten into the discipline. You've basically gotten into the discipline groove that you need. So I don't know if you're going to think this is too terribly hard, but whatever the reason, this coming Sunday is December 5th. This coming Sunday, you have a pretty hefty simulation due, but it's not going to be crazy. And the chapter 31 homework is not due this Sunday, but the following Sunday. So just as long as we're here, here's our remaining semester. Sunday, December 12th, chapter 31 homework. Yeah, so we're definitely close to the end. So we actually have a little bit of breathing room towards the end. So that what I'm going to do is I'm going to go back and recycle chapter 28, 29, and 30, because I mean, it's been a long time since we've touched chapter 28. And a chapter 28 problem may be on the 4th exam. Maybe it will, maybe it won't. So just wanted to call that out just in case that puts you in a good mood, because it puts me in a good mood anytime I hear that I have more breathing room. All right. So here's the impedance. This is the aggregate result of capacitive reactance, inductive reactance, and resistance. This is the aggregate result of all of these resistors. Now, as I was saying before I kind of sidestepped here, probably the most challenging part of chapter 31 is this notion called phasors. Is this entity known as phasors? Technically, some of you have seen phasors before in chapter 16. I'm going to go back now, and I don't typically do this on a Tuesday Zoom class, but I will now, because the more times I can throw this at you via Zoom and in the classroom and on your own without me in the picture at all, the better off you're going to be, I think. So let me just take let's just take a little bit of a tour through the chapter 31 green sheets. And here, let me play this. Stand in for the circuit current. All right. Okay, here's a phasor diagram animation that represents all four elements: the EMF, the resistor, the inductor, and the capacitor. Go through this carefully and recognize the inductor phasor leading the current phasor, which is proximate. Anyway, look how complicated that looks. But if I back up, what's going to happen in this lecture video? This lecture video will take you through the whole thought process behind phasors. And I'm going to get, and I don't want here. All right. So what we're going to do, what the video does, it says, let's look at every element in an RLC circuit: the resistor, the inductor, the capacitor. So here's just a little sample. I'm not going to play this from beginning to end, but here's how a resistor behaves. Ready, set, go. Phasor and the black current phasor are always aligned. There's no shifting between these two signals. You can see they both rotate in a counterclockwise direction, and that's convention. The length of these vectors corresponds to their magnitude or maximum values. And check out their projections on the y-axis. The magnitudes of those projections indicate the voltage value and current value at any particular time. Carefully study. All right, anyway, so this was step one. This is looking at what's going on when you subject a resistor to alternating current. And you can see how this brown arrow and this black arrow are synchronized, and you can see they're rotating counterclockwise. What is the rate with which they rotate counterclockwise? That is determined by the voltage source, by the generator. Again, you were creating your own voltage source when you had the magnets and you were shaking them back and forth. This rate, this oscillation value is determined by the power company, or you as an electrical engineer, you would design this. But you can see it's moving, it's spinning counterclockwise. So this is a fancy way of, so these are phased vectors. This is a vector diagram, which means you have to worry about direction and magnitude. And not only that, but we're worried about the phase between these vectors. So you can see there's no phase. The phase angle between black and brown for a resistor is 0. So a resistor is completely synchronized with the power source as far as the current flowing through it is concerned. So let me go up maximum value and then fast forward. Capacitor and see about phase shift. Capacitor current, and shift. All right, so here leads its full shift between. All right, so now we're stepping through. So that was, and again, I'm assuming you're going to watch these lecture videos many times. I'm giving you like the speed of light version. So we talked about how does a resistor behave when it's exposed to alternating current. Now the next question is, how does a capacitor behave when it is exposed to an alternating current? Check out the phasor diagram. Blue is the capacitor voltage. Black is the power supply, or the AC supply voltage, the EMF. So just let's take a visual on this. Check this out. Capacitor current and capacitor voltage. Both the phasors are rotating counterclockwise, again, by convention. And you can see that here for capacitor, the black current phasor leads the blue voltage phasor by 90 degrees. Once again, the length of both these phasors indicates the maximum value of current and voltage. And at any moment in time, t, their projection onto the y-axis indicates their values at that instant. Here's a good... All right, so hard at first. This might be complicated. Maybe it's not. Maybe it was just complicated to me at first. But I think this was the type of thing that I kind of had to look on. This was the type of topic that I had to study this multiple times, spread out over multiple days, if not weeks, before it started to really sink in. But the phase angle between the capacitor and the AC supply is 90 degrees. And you can see, as mentioned, the current, this black vector is actually leading. It's leading the capacitor voltage. So just so you can see that. Both the phasors are rotating counterclockwise, again, by convention. And you can see that here for capacitor, the black current phasor leads the blue voltage. So last but not least, let's look at what happens when an inductor is subjected to AC circuit. Here it is. Relationship. Here's the animated phasor diagram for an inductor's current and voltage. The black phasor represents current and the green phasor represents voltage. They both rotate counterclockwise, which is the convention. Their angular frequency. All right, so you're thinking this looks just like a capacitor, but the difference is this green vector is leading the current vector. This green vector represents the voltage across the inductor when it's exposed to alternating current. And this black vector represents the current, and you could also say the voltage as well, because Ohm's law says current and voltage are related. All right, so when you put these all together, when you put the RLC all together into a single circuit, this is actually nothing more than pasting together those three previous animations. Diagram animation that represents all four elements: the EMF, the resistor, the inductor, and the capacitor. Go through this carefully and recognize the inductor phasor leading the current phasor, which is proxied by the resistor voltage. So pretty involved stuff, but that's I just wanted to take the opportunity to nudge that in there. So I don't know how well you heard that, but because I wasn't sharing the sound, but this is sort of a good summary page here. In some ways, this is chapter 31 at a glance. So I don't typically like to do this. I don't typically like to say, well, you can kind of ignore everything and just make sure you know what this says. I mean, to me, that's not a good practice. Why would I say that? But I will say is you should tap into everything from these Zoom classes and the Thursday classes and the lecture video and rewatch the Zoom recordings to make sure this page makes complete sense to you. Okay. So if you look at, let's just take a look at this phasor diagram right here. Let's just look at this phasor diagram right here. If my voltage across the inductor is greater than the capacitor, we don't really care about that right now. Right now I'm saying, hey, this is where this expression for impedance came from. Remember, impedance Z equals the square root of R squared plus XL minus XC squared. Where did that come from? It came from Pythagorean theorem. So just to see the birth process of impedance, this is my voltage across the resistor right there. This is my voltage across the inductor. Notice how the inductor voltage is leading the current by 90 degrees. So this is going to always be 90 degrees. Okay. This right here is my voltage across the capacitor right here. So this is all explained in detail. I mean, I'm explaining it a bit, but the deep dive is, again, in the lecture video. This theta L is always going to be plus 90 degrees. So this is always going to be plus 90 degrees. This is always going to be negative 90 degrees with respect to the current going through the circuit or the voltage drop across the resistor. So this I value and this R value, again, these are always aligned because the voltage across the resistor is always synchronized with the current going through it. All right, so this is where Pythagorean theorem comes from. I have a right angle triangle. Here's 90 degrees right here. That's 90 degrees. So if I do Pythagorean theorem on this triangle right here, I'm going to get, well, okay, I'm going to get E squared equals VR squared plus VL minus VC squared. And this right here, I have my voltage drop across my inductor going in that direction. In the exact opposite direction, I will always have my voltage drop across the capacitor. So if I take this vector and I blend it together with this vector, they're always going to be offsetting. These are always going to be fighting each other. They will always offset. In this particular case, when they offset, this is the offset value, VL minus VC. Okay, so again, thanks to Pythagorean theorem, this is what we get in terms of this right angle. Now, what I will do now is I'm going to go up to each one of these elements and divide through by current. And I'm going to remember Ohm's law. Here's Ohm's law, V equals IR. So if V equals IR, you know what I can say? I can say R equals V over I. All right, so I'm going to go up to each one of these voltage values and divide through by current. Ready? I'm going to divide this value by I. So EMF divided by I. I guess I use capital letter I, capital letter I. I'm going to divide this value by capital letter I. I'm going to divide both of these, VL, divide that by capital letter I, divide that by capital letter I. So if I go through each one of those and I divide through by capital letter I, and I need to clear that clutter because that got kind of crazy. I'm dividing this value by current, this value by current divided by I, this value by current, and this value by current. So what does this become when I divide this by current? Well, Ohm's law says that's resistance. Resistance for an inductor is X subscript L, inductive reactance. Resistance for a capacitor is X sub C. And then this is basically just R right here. Ohm's law says this is R. Okay. And this would be Z. Okay, so there, I didn't do anything to this phasor diagram other than divide through by R. I'm sorry, divide through by I. So if I did this same Pythagorean theorem here one more time, I would say, well, okay, I divided EMF by I, which is Z squared. Z squared equals R squared plus XL minus XC squared. And that's where you get basically impedance. Okay, lots going on. This is heavy stuff. But there's not an infinite amount. This is, I don't know if there's anything there's a couple of new introductions that have to be made, but this is kind of it. And you might say, well, Chris, you're saying this isn't a ton of stuff, or we're done with the new stuff, but I don't understand any of it, that's my common answer. Like, oh, great, so there's not a lot more new concepts to digest, but I don't understand any of these, but that's where time heals all concerns like that. All right, so I'll say it one more time. Your goal is to go through the green sheets and the YouTube lecture video so that by the time you're done, everything you could teach this page. I call in sick and you take over and you could explain this page to your own crop of physics students. Easier said than done, but at least we're not rushed. Okay. And if the resources that you have at your disposal are clear, it's really not too crazy. All right, so let's do the quiz. That was a whole bunch of new introductions. So here's the situation. Part A says, for this RLC circuit that is now being powered by the fine people at DTE DTE energy or consumer's power. Part A says, what's the capacitive reactance? All right. And believe it or not, at this point, this problem will kind of go fast. Number one, part A says, what's the capacitive reactance? And we know I have now introduced capacitive reactance. It's omega D over C. So let's keep going with that. Equals, well, maybe I'll just say omega D equals the driving frequency. Let me get a picture here. Siemens electrical turbine generation. So let me just see if I got some pictures here. This is pretty good. Yeah. Let me open this in a better and share it. Check this out. So here is a natural gas powered turbine right here. So this is what spins. These things are monstrously impressive. This is a small one. They get far bigger than this. And you can see that even though this is a small turbine, look how big it is. And these are exposed to really hot gases that come from really hot combusted natural gas. Sometimes they're exposed to jets of steam, and that steam comes from a coal-fired plant, but coal is kind of being phased out and shut down. So sometimes steam comes from coal, heating up water and boiling it. Sometimes steam comes from nuclear power, which heats up water and boils it. Or most commonly, these turbine blades are being spun around like a flywheel, like a pinwheel, via jets of very high velocity combusted natural gas. And it's that natural gas that just basically is aimed at these fan blades that makes it turn. And this is where you get the driving frequency. This is omega subscript D. This is the rotational velocity of this spinning turbine is what we call angular frequency. So back to the problem. All right. Now you know where that comes from the power plant using that gigantic turbine. All right. So the driving frequency is, well, it's going to be equal to 2 pi f, birth of a radian. Okay. So now if that's the driving frequency, I can say this. The resistance caused by the capacitor, and I shouldn't say the resistance caused by the capacitor, I should say the capacitive reactance, which is basically an impedance to the flow of current, is equal to 1 all over the driving frequency, which is 2 pi f, times the capacitor value, which for me is 24.7 e to the minus 6 farads. So that becomes 1 over 2 pi f. And for me, that turbine is spinning at a rate of 394 spins per second. So F is 394. Technically, the units are hertz, and a hertz is the same as a reciprocal second. So that's my driving frequency converted from a linear frequency to an angular frequency times 24.7 e minus 6 farads. I'm not doing the dimensional analysis, which is something that is very helpful. So what is all of this? 1 divided by 2 divided by pi. $16 and some change. 16 point, and the units work out 16.354. The units do work out to be ohms. So I'm thinking there's so much new stuff coming your way that maybe I'll just set aside some separate time to talk about unit conversions and dimensional analysis. But here, this is at least consistent. I kept yammering on about how a capacitor does introduce a kind of electromagnetic resistance, and the units are ohms. So I'm going to put that in calculator memory location A, just because you never know. You never know what you might need later on. Okay, that's part A. Done with part A. Ohms. What's the impedance? So I'm going to go way over here. Number 4. Number 4. What's the impedance? Z. And I'm going to rant again. Z is the overall resistance to current flow current flow is redundant. This is the overall resistance to current due to the capacitive resistance, which is really better termed capacitor reactance, the sort of the resistance or the reactance brought about by the inductor, and the resistor, the physical. So this is electromagnetic in nature. This is electromagnetic in nature. This is physical in nature. I know I said that before, but right. So we need to find out what is the total resistance here. It's Z equals Pythagorean theorem. Pythagorean theorem brought us to this point, R squared plus XL minus XC squared, which begs the question, what's XL? XL is inductive reactance. This is the inductor's resistance to current flow, and that equals omega D times L equals 2 pi F. That's the driving frequency brought to you by that gigantic fast spinning turbine times L with numbers 2 pi F. For me, my turbine is spinning at the rate of 394 cycles per second, also known as a hertz, times that's 2 pi F, and L. My inductance here is 149 millihenry. 149 millihenry is just 0.149 Henry. So I'll just do that kind of on the fly. So this is XL, and I'm going to put this in calculator memory location B. Okay, right. So let's get a number on that. And I got to put that store alpha A. I have XC and A, and here's XL, 2 times pi times store alpha B. All right. And numerically, I'm getting a value of 368 and some change. And that would be omega. So they didn't ask for it. I'm just going to double check store alpha B. I'm getting the same number twice. All right, so number 7. Number 7. I'm going to move some stuff around. Okay, here's number, I'll put number 7 over here. I'm going to get rid of this. So part B says, what is the overall impedance of this circuit? Here's number 5 again. Number 5 says that impedance is going to be the square root of R squared. And for me, my R is 228 ohms. So let's square 228 ohms plus, and here's Pythagorean theorem, the other side of that triangle, which is the difference between the inductive reactance and the capacitive reactance, because they're always fighting each other. So this was just going to be calculator memory location B minus calculator memory location A squared. So let's see what that looks like. $419 and some change ohms. I'm going to put this in calculator memory location C. Store alpha C. So just a brief respite. I know the resistance to the current due to that resistor, due to that capacitor, and due to this inductor, as they are all simultaneously subjected to this power source from DTE energy or wherever it comes from. That's part B. Part C says, what's the current amplitude? So part C says, what is the current amplitude? And again, I sub M is referred to as current amplitude. Current amplitude, whenever you have amplitude, whenever the word amplitude is used, it's saying what is the peak most value, knowing that the values vary from some peak value all the way down to 0 to some negative peak value. But this is current amplitude. What is the peak current flowing through this circuit? And if you're an electrical engineer, you want to have, you want to be aware of what the current is going through the power grid. Or if you're a computer engineer, you need to be aware of current flowing through a circuit, right? The current amplitude, and this is Ohm's law. Ohm's law to the rescue. Ohm's law to the rescue. Ohm's law says V equals IR. If V equals IR, then I is going to equal V over R. If V equals IR, that means I equals V over R. So that's true. That's Ohm's law. Now let's personalize Ohm's law. So this is personalized. Let's personalize Ohm's law for AC. Ready? Here goes. It's I equals V over R now becomes the current magnitude is the peak EMF all over the impedance. So that is analogous. We can use that. So I'm saying, all right, so current in Ohm's law, yes. We're just dealing with max values. So the maximum value of current in a regular old simple DC circuit was just voltage right here, voltage. And instead of saying voltage in an AC circuit, we call it EMF, maximum value, divided in the good old days with simple DC circuits divided by the circuit resistance. But in the new world here, we refer to impedance. Okay, but here's the good news. The good news. This is Ohm's law for simple DC. This is Ohm's law for AC. So let's just take advantage of that and solve for the peak current going through this circuit. Number 11. The current amplitude is going to equal the EMF, which for me is 221 volts. 221 volts is the peak voltage supplied by my power provider, my turbine power generator, all over Z. And I just figured out Z. Z is sitting there in calculator memory location C. So that looks pretty good. Let's just take what is 221 divided by alpha C? 0.52 and some change. 0.526 for whatever amperes, and that can go into calculator memory location D. That's it. And that obviously all of this is important to know. Obviously, you need to know what's going on with voltage, with impedance, with current. Otherwise, we can't turn on our appliances and personal electronic devices. That was C. Oh, that, believe it or not, we're kind of done with this. But this is interesting. It says a second capacitor is then connected in series with the other components. Interesting. So this is what's going on. We are going to add another capacitor right here. All right, so this is a second capacitor in series with everything else. Let's see, it says a second capacitor of the same capacitance is then connected in series with the other components. What happens to capacitive reactance? What happens to impedance? What happens to the current? All right, so I know I can remember this. I have two capacitors in series with each other. So the equivalent capacitance is going to be 1 over C plus 1 over C, or the equivalent capacitance when I add the second capacitor is going to be 1 over 24.7 microfarads. I'll just write it U for microfarads, plus 1 over 24.7 microfarads. So this is what happened. This is what happened to my capacitance. What is 1 divided by 24.7 plus 1 divided by 24.7, reciprocal that whole thing, 12.35. So we have to ask ourselves, if the equivalent capacitance now has decreased, if it's gone from 24.7 microfarads down to half that value, 12.35 microfarads, what happens to the capacitive reactance? So let's do that. Number 12. So I am focusing on part D. What is the new capacitive reactance? And the answer is, well, here's what it is. It's X sub C equals 1 over C is in the cellar, omega D times C equals 1 over 2 pi times 394 hertz, which is reciprocal seconds, over my new capacitance value, which is 12.35, my numbers, 12.35 e to the minus 6. So I can kind of see what's going to happen, but I'll do it. Here's my new capacitive reactance. It's going to be 1 divided by 2 divided by pi divided by 394 divided by 12.35 e minus 6. 32 and some change. So it doubled. X sub C equals 32.7 ohms. 32.7 ohms. So aha, this is a big aha. X sub C increased. Is that what they say too? Yeah. So X sub C increases. So when you reduce the capacitance, you basically increase the resistance that is caused by that capacitance. And I really shouldn't say resistance anymore. I'm going to refer to the term reactance or sometimes impedance. But why did the resistance increase? Why did it increase? Because I have less capacity. So if the job of my AC, my EMF, my power supply, if the job of my EMF is to crank current through the circuit, if my capacitor decreased, that has reduced its ability to accommodate charges flowing onto it and then off of it. So that's why my capacitive reactance has increased. That's part D. Part E says, what happens to Z? So we can kind of motor through this. So just let's redo number 7. Here's number 7 again. So your overall impedance, and you can kind of see where this comes from, but let's see. The overall impedance is going to equal to square root of R squared plus XL, which is unchanged. So that's still sitting there in memory location B, minus, I better store this. This is store alpha E. Okay, minus my capacitive reactance, store alpha E. That's all squared. So here's my new impedance, 228 squared plus alpha B minus alpha E, quantity squared, square root of all of that, 406. I decreased 406.18 ohms. So this is a decrease. So we need to talk about this. My capacitive reactance increases. So that's now less friendly to current flow. But my overall impedance, decreases, which sounds weird. How the heck? Why does my overall impedance decrease when I just got done saying, hey, the capacitor is actually more resistant to current flow? So how do we reconcile that? But for now, I mean, the numbers don't lie. My Z value, my impedance is actually 406, whereas before it was 419. So I went from 419 to 406. That's a decrease. How does that happen? And the answer is right here on this page. Boing. Apparently, what's going on is my capacitive reactance is actually coming closer to match the inductive reactance. That's called impedance matching. So this is a good thing. If you can basically finagle or tune things or customize things so that this capacitor behavior is actually coming closer to perfectly offsetting this inductor behavior, you will increase the net result. So imagine if this went down to 0. If you had a perfect matching between the inductor behavior and the capacitor behavior, this orange vector would actually get longer. It would be as long as it could possibly be. Okay, so that's what happens if you have this matching between the inductor and the capacitor, which is what we have going on here for this particular problem. So that's why the answer is decrease. And you know what? We don't even have to do calculations for part F. You could argue we didn't need to do calculations for any of this, but if my overall circuit impedance has decreased, what is Z? Z is impedance. So Ohm's law is saying, hey, if your net impedance due to the resistor, the capacitor, and the inductor, if this just decreased, Ohm's law says that V equals IR, which means I equals V over R. And if we personalize this for AC circuits, the max current is going to be the max EMF over the net amount of resistance. If Z decreases, if you figured out how to decrease the impedance, this is now smaller, the net result is the current has just increased. I sub M increases. So the real takeaway here is, boy, that seems weird. Again, if your head is still, if you're still in the throes of an emotional trauma, because how can you increase the capacitive reactance and yet everything gets better? How can you make the capacitor more stubborn and yet everything gets better? The answer is because it's a blend. You always have to blend together what's going on with the capacitor against what's going on with the inductor. And this is a real thing. Check out this. You guys, maybe you'll notice this going forward. Maybe have you driven by any power plants like this and you see junk that looks like that? This is a bank of capacitors. Or maybe you've driven past and seen stuff like this. This is like on a telephone pole, not far from where I live.
We're still looking at the problem.
So anyway, thank you very much. So to conclude, maybe you've driven past junk that looks like this. Just this, it looks like alien equipment. It looks like equipment from a science fiction movie. So you've seen these are sometimes clustered together and in set aside areas. And as I was saying, thanks for the heads up. Maybe you've seen telephone poles with more alien equipment. These are capacitors. And so what happens is engineers add capacitors or take away capacitors so that they get this balancing effect, because the goal is to balance the capacitors with the inductors in such a way to increase efficiency. So that is hopefully going to be remembered by you next time you pass by this junk. Stuff. All right, so let's do this. Here's the problem. 10:01. See you at 10:07 a.m. Okay. Next, chapter 31, quiz 4. Should look like this. Let me know if it doesn't. Okay. Another RLC circuit. This isn't gonna, well, so say this looks pretty easy, but I'll find a way to squeeze out every last drip of learning value because there's some new things here. Number one, well, an RLC circuit with a generator. So here's the generator. This is the generator, consumers power, DTE energy, some nuclear power plant, whatever. Here's a resistor. Here's an inductor. And here's a capacitor. So there are 4 elements: the generator, generating the EMF, R for resistor, L for inductor, C for capacitor. RLC circuit with a generator. In an RLC circuit, can the amplitude of the voltage across an inductor be greater than the amplitude of the generator EMF? And the answer is yes, but let's talk about that. So let's go back to this visual here. Let me actually take a snip of this and bring it into our quiz. Okay, so referring to this phasor diagram. Okay, so for part A, well, let's see. The question is, can the voltage across an inductor? So this is the inductor voltage right here. This is the voltage across the inductor right here. Can that ever be greater than the amplitude of the generator EMF? And your first, if you're like me, your instinctive, your gut response, your knee-jerk reaction is, of course not. How could I have, for example, how could I have a voltage across an inductor be, say, something, just for example, be 100 volts and my EMF be 50 volts. That's impossible, right? That violates conservation of energy and common sense. Well, conservation of energy. So your knee-jerk answer is no, that can't happen. But then you study phasors, phase diagrams. And let's see, well, what if I had a situation where I had, well, this is kind of a good situation here, but I'm going to, here, let's do this. So here, let's make up our own little custom phasor diagram. What if I had my the voltage drop across my inductor look like this? Some arbitrary, at some arbitrary point in time, just freeze framing it at some arbitrary point in time. Okay. What if I had, and I know that's always 90 degrees ahead of my current voltage. So this will be 90 degrees because, and there's an acronym, I'll throw it out now. Eli the Iceman. Eli the Iceman. Eli the Iceman is a common, it's been around since the year 400. It's a really old mnemonic. Eli the Iceman. Eli the Iceman is basically saying for an inductor, voltage leads. E stands for voltage. Voltage is leading current. Eli, E comes before I. Voltage leads current for an inductor. For Iceman, this means current. I stands for current. Current is ahead of voltage. So current leads voltage for a capacitor in an RC circuit, an RLC circuit. All right, so Eli the Iceman, very well-known acronym. This is my voltage across my inductor. This is the current going through the resistor. So this is actually a good time to reiterate some key points. This is current. So my purple is the current, but my red is the voltage, or orange, I should say. This is my voltage drop. So this is my voltage across the resistor, whereas this purple is just the circuit current. And the circuit current is the same everywhere. So, and then what if I had a capacitive reactance, or I should say a voltage drop across my capacitor like this? How should I draw it? Well, I know it's 180 degrees away. So what if I had maybe something like that? So this is my voltage drop across this capacitor right here. So I'm referring to the voltage drop across the resistor, across the inductor, and now across the capacitor. So this is my voltage drop across the capacitor. All right. So now if I let me fix this a little bit, because this is okay. That's good. So Eli the Iceman says that that's a 90-degree angle. And you know what? That's a 90-degree angle. So if I did the vector addition on this, I would say, well, okay, I'm going to have this black vector. So I'll take a copy and paste. Here's my black VL vector. And I got to go tail to head. So it's the same old vector addition, tail to head, tail to head. So that goes right here. And then it's being offset by this red vector, because remember, these are always 180 degrees out of phase. So it's offset like this. Okay. So what's the net result? Let me move some things around. Okay. This is right here. This is going to be VL minus VC. And here's the net result. First tail to last head. I will use blue. Here. Okay. Ready, set, go. There. Okay, so this is going to be my EMF. Brought to you by Vector Addition. This is going to be my EMF voltage. So there it is. Look how large my voltage drop is across my inductor. Look how small this blue vector is. The magnitude of that blue vector is clearly much less than the magnitude of that black vector. So the answer is yes, you can have a voltage drop across this inductor that is larger than the actual power supply itself. We just showed that right here. And if you're wondering how this can happen, the answer is because, well, at any point in time, like right here, if I stop at this, at t equals 1.2 seconds, just for example, yeah, I have a huge voltage across my inductor, but it's being offset by the voltage across the capacitor, and the net result is reasonable when you combine it with the resistor. All right, so that's why this answer is yes, as illustrated by this phasor diagram conversation. So now the question is, what's going on at resonance? Okay, so this is a great time to talk about what resonance is. I might not even have to erase anything. So part B says, what's VL? At resonance, a very special term. At resonance, VL equals $. And now a word about resonance. Let me bounce out of here into Falstad. Okay. All right, so here's if I go into Falstad, I'm going to pull up a circuit that they have stored. What AC circuits, series resonance right here. Look at this. Here you're looking at you're looking at the same circuit, basically. Let's talk about this. So 3 RLC circuits, 10 ohm resistor in all 3 cases, 15 microfarad capacitor in all 3 cases, a 1 Henry inductor in all 3 cases. Let's look at the power supply. This EMF has a max voltage of 5. This EMF has a max voltage of 5. And similarly, the bottom circuit EMF has a voltage of 5. So you're looking at 3 different circuits, identical in every way except for one, the driving frequency. This generator is operating at 35 hertz. The bottom generator is operating at 45 hertz. This middle generator is operating at 41.1 hertz, which is actually the perfect result. So watch what happens when I hit reset. Ready, go. So you have reactions. You have voltage drops across the top. So this left graph is showing what's going on at the top. This middle graph is what's going on in the middle, and the right graph is what's going on at the bottom. So again, side by side, left is top circuit, middle is middle circuit, and the right graph is the bottom circuit. And I'm going to speed things up, and I'm going to keep my eye on, well, even now I can see it. Check this out. Look right here. Look at my left circuit. My left circuit is corresponding to the top. My left graph is corresponding to the top circuit. Look at the maximum voltage I've attained. I'm going to speed things up. Well, this maximum voltage is 18.924. My middle circuit, 125, and my bottom circuit, 25 volts. So, and this is a head scratcher because you're saying These are identical in every way in terms of max voltage supplied by the EMF, the R values, the L values, the C values. The only thing that's different is this frequency. And if I speed things up, maybe I'll just go crazy like that. So look at the left, 18. So 18 volts at the top. So that's kind of anemic. My middle, though, I'll stop that because that's kind of crazy. My middle circuit is exhibiting 129 volts. And again, I guess we're looking at what's going on across the capacitor. So when I hover my mouse to this left graph, notice how that top right capacitor highlights. When I hover my mouse over the middle graph, notice how the capacitor in this circuit highlights. And then on the very right here, it's highlighting the rightmost capacitor in the bottom circuit. So I'm looking at the capacitor voltage just as a way to figure out what's going on. Hugely better, hugely stronger result for this middle RLC circuit. So 41.1 hertz is matching, is basically matching, is the magical resonance, is the magical frequency. If I can drive a circuit, if I can drive this circuit at 41.1 hertz, that's the magical value. And magic means resonance occurs, and resonance means maximum amplitude response. And that's a chapter 15 that goes back to physics 211 or your prior physics class. So that's what resonance is. You're seeing that right here vividly, 18 volts versus 129 volts versus 24 volts. All right, so now that's resonance. And it seems like resonance is a good thing. Wouldn't you want things to work harmoniously like that to get like the maximum efficiency? And the answer is most times for sure. That is, resonance is something that you often want to achieve. All right, so having said that, what's the resonance? What's the voltage drop across this inductor at resonance? So I better clear the deck here. All right, so at resonance, you know what happens at resonance? XL equals XC. That's the magic of resonance. At resonance, you basically have the inductor and the capacitor mutually destroying themselves. So that means, hey, that means that their resistances, the reactance of the inductor is not a friend to current. And similarly, the reactance of a capacitor is not friendly to current flow. If you can get them to perfectly offset, though, then that's the friendliest situation you can hope to achieve. So up here, again, what happens if I divide through by I? I'm going to divide this by I, the circuit current, divide this by I, which is, again, the circuit current, divide this by I, which is the circuit current, and divide this by I. So if I do that, if I divide everything by I can just, here's the equivalent phasor diagram. Instead of representing voltages, I can use it to represent reactances and resistance. So if I divide this by I, this becomes X subscript L. If I divide VC by I down here, this becomes X subscript C. This is just Ohm's law. So this is X subscript C. And if I divide VR, if I divide this voltage drop across my resistor by I, that's just R for resistor. So this is the same phasor diagram, but with resistances and reactances. And last but not least, if I divide this EMF value by R, that's the impedance. Impedance is the aggregate result of the reactances and the resistance. All right. So if I play my cards right, if I can get XL to be the same as XC, I'm going to have a perfect offset of these reactances, and my my reactance will actually be as small as it can possibly be. I'm trying to get that arrow. So check out what happens if this red vector right here was perfectly offsetting that black vector. If XC equals XL, then check out what happens to my impedance. My impedance actually shrinks. My impedance is actually as small as it's ever going to be. So when I have XL equals XC, my impedance attains its most minimum value. Its minimum value. So min. Z equals its minimum possible value when XL equals XC. Great news. That's called resonance. You're going to get the greatest amount of current, the greatest efficiency. So number 3, XL is omega D times L equals 1 over omega D times C. This is my inductive reactance. So let me just be repetitive. This is XL equals the driving frequency times the inductance. This is X sub C. Okay, so anyway, I think I'm making my point here. Well, all right. C is in the cellar. That's how I remember that. So let's solve for omega D. Let's solve for the driving frequency. Number 3. So omega D squared equals 1 over LC, which means the driving angular frequency is going to equal 1 over the square root of LC. That's that. All right, so let's get a value on this. All right, so the resonant frequency. So this is the resonant driving alternating current frequency. And at this value, at this results in Z equals Z min. And check this out. If this inductor reactance cancels this capacitive reactance, the only resistance that's left, the only resistance you have left is just the resistor right here. Oh, that's not good. The only thing that's left is the resistor value. So Z min at resonance, Z min is basically just the R value equals R. Okay. Number 6. Oh, we're getting a number on this. So omega D equals 1 over the square root of L, which for me is 0.9 Henry, 0.9 Henry times the capacitance, which is 1.2 e to the minus 6 farad. Whatever that is, let's put it into calculator memory location A. Okay. 962 and some change. Store alpha A. 962 radians per second. Not that we need that. So if I can drive this current at this magical frequency, if I can spin that turbine at just this perfect value, 962.25 radians per second, I'm going to get resonance And at resonance, this is the voltage drop across my inductor. Ohm's law says V equals IR. So I equals, I don't know what I is. So V equals IR equals I times R XL. Okay. So I guess, did we figure out I yet? No, at resonance, find the amplitude of the voltage across the inductor. So this is what I have in step 8 is Ohm's law. I'm going to get I times XL. So XL is omega D, and I have that, times L. But before I guess I go any more, I got to figure out what I is. All right, so number 9. Number 9. In general, Ohm's law says V equals IR, which means I equals V over R, but personalized for AC circuits. This is what the maximum current is. The maximum current is V, but it's the EMF all over Z. Got it. Let's keep going with that. Do I know the voltage? I do. It's 8 volts. So it's the EMF from your power, from your generator, 8 volts, all over this thing again. Pythagorean theorem, square root of R squared plus XL minus XC, that squared. But aha. So there's a huge aha here. Number 10. At resonance, XL equals XC. So you have this impedance matching. You have the impedance of the inductor matching the impedance of the capacitor. Going back to this visual right here for the umpteenth time, if you can figure out how to match those two impedances, that is the most efficient you're going to get, unless you can figure out how to eliminate that R value resistance, and maybe you do a superconductor. All right, but at resonance, this whole term, so low-hanging fruit, this goes to 0 because XL equals XC. So this is the current. This is the maximum possible current going through this circuit. Current equals the EMF, maximum EMF, maximum current amplitude equals the EMF amplitude, max values, all over R. So that is Ohm's law for sure. My EMF value, my peak voltage is 8. Again, it might be 4.2 or negative 3.9, but the peak value is going to be 8 volts divided by my resistance, which for me is 10 ohms. And that's equals 0.8 amperes. So number 12, let's read back to number 8. Number 8 now becomes the voltage drop across that inductor equals 0.8 amperes. That's the I value. So I'm going back here. There, I know, and I should write, this is I subscript M. This is current amplitude. Got it. Maximum possible value of the current. And then omega D is sitting there in calculator memory location A. And the value of my inductor is 0.9 henries. So I have times 0.8 times 0.9, 692 and some change. 0.82 volts. So check that out. 692 volts is the voltage drop across the inductor. And how the heck? Because the EMF, 8 volts. 8 volts is the maximum voltage provided by the EMF. How is this possible? Once again, because you're offsetting you're offsetting this voltage with a negative V sub L. So V sub C offsets this. Just to make sure we haven't lost our minds. Okay. Okay. Time check. 10:36. Okay. Let me get the next one ready. Chapter 31, quiz 5 is 46. Okay. Chapter 31, quiz 5. I hope looks like this. An AC source, an alternating EMF source with a variable frequency is connected in series with, oh, look at this. We don't even have an inductor. We have an RC circuit. So this looks like a chapter 27 type thing, but let's see. An alternating EMF source. So here's your power supply. This is your voltage source. That squiggly line means like a sine wave or a cosine wave. And then what do we have? It's connected in series with a resistor and a capacitor. There's no mention of an inductor, but I mean, we have all the building blocks now. That's the beauty of surviving the learning phase, which if you're like me, it takes days to get up the learning ramp for something like this. But this is my EMF. This is my resistor. This is my capacitor. There's no mention of an inductor, so I'm not going to draw it. Okay, consider a phasor diagram. All right, so let's do the phasor diagram. Ready, set, go. All right. Consider a phasor diagram for the voltage drop across the resistor. So I'm going to do it at some time t. So I'm going to say at some time, at some arbitrary time t. All right. So this is my, all right, this is my voltage drop across the resistor. I guess I'll use green for that. All right, and you know what? I need to start drawing too. This is in the source material in the video, but this at some time t, you know how I represent that right here. This is theta equals omega, the driving frequency times time. Okay. So this is my voltage drop across the resistor. And this was, I said this a couple of times and it's said a lot in the lecture video and the green sheets, but the current's the same everywhere. So if I have the current, whatever the current is going through the resistor, it's the same going onto or off of the capacitor. And if there were an inductor here, it would be the same coming into or coming out of the inductor, going through the inductor. So that's the great unifier, is I stands for current is the same everywhere at all times. So that is a good fallback position. The current is the same everywhere at all times. Things change, like you have all of these voltage, you have voltage shiftings, you have all these phase shifts going on, but the one unifier, like the one master clock, is current. All right. So anyway, at some arbitrary time t, there's the voltage drop across my resistor. If I had an inductor, which I don't, but if I had an inductor, I'm just going to do it for the sake of reinforcement. If I had an inductor, Eli the Iceman says the inductor voltage leads that's not good. So the inductor voltage leads the EMF by 90 degrees. I'm looking for, all right. Still not what I'm looking for. Okay, here. Okay, that's fine. All right, so this is V subscript L, which technically is non-existent, but I'm just doing that here for reinforcement. And then my capacitor looks like this. My capacitor voltage is always opposing. So this is V subscript. And let me make this obviously different size. I don't mean to make those similar in size, because that's not necessarily the case at all. So right there, okay. This is V subscript C, the voltage drop across my capacitor. Eli the Iceman says, well, I'm looking at ice. Ice means for capacitor, current leads voltage across the capacitor. Voltage is signified with the letter E. Current leads voltage for a capacitor. C for capacitor. All right, so that's why the current, there is no phase shift between the current and the voltage drop across the resistor. That's why these are always lined up. You're always going to have this current vector, this purple current vector, and this green resistor vector are always going to be perfectly in phase, whereas this is always going to be 90 degrees. And this is always going to be 90 degrees. All right, so anyway, that's a phasor diagram. Consider a phasor diagram for the phasor VR. So I got that. I have a visual for VR. Yes. And VC. Here's VC. This doesn't exist, but it's there just for a healthy high fiber diet. I'm crossing it out though. Consider those two phasors, a phase vector. At what driving frequency do these two phasors have the same length? So number one, at what driving frequency at FD equals $, does VR equal VC? Question mark. Okay, so number two. Well, I know that VC, according to Ohm's law, VC equals I times R, but I don't write R for capacitors, X sub C. And I know the voltage drop across the resistor is that same I value times R, like that. So if I set them equal to each other, if VC equals VR, because it says at what driving frequency do these phase, let me back up. At what driving frequency do the two phasors have the same length? If VC equals VR, then I guess I'm saying the following. Here's VC, IM times XC equals IM times R, just because this is VC, this is VR. Low-hanging fruit, IM here cancels with IM here. Number 4 says XC equals R then. This is when I have this, if they're the same length, they have the same reactance value. The reactance of the capacitor is the same as the resistance of the resistor. So that means 1 over omega D times C, because this is, remember, capacitive reactance was found to be 1 over omega D. We actually derived that, I think, in the last problem. Well, no, this is in your, this is a definition introduced in the green sheets in the lecture video. So this is the capacitive reactance equals the resistance R. Okay. Number 5. What am I solving for? I'm solving for the driving frequency. So that means omega D, and by the way, omega D does still equal 2 pi F, birth of a radian. Omega is 2 pi over T, or 2 pi F, since F and T are always reciprocals. So I have omega D is going to equal 1 over RC. Okay, that's good. So let's isolate F. F equals 1 over 2 pi RC. Is all of this making sense? Okay, I guess so. So let's find out the driving frequency that makes those phasors the same length. The driving frequency that evenly divides the voltage drop across the resistor and capacitor. 1 divided by 2 divided by pi divided by R divided by C. 108 and some change. So again, this is the magical frequency. Well, it's not that magical, really. It's just, hey, at this frequency, the voltage drop across your capacitor right here. So the voltage drop VC is going to be the same as VR at that particular frequency. Hertz. I don't know if I need this, but I'm going to stick it in memory. Store alpha A. Part B says, at that driving frequency, so I guess I really do need to save it. At that driving frequency, what's the phase angle in degrees? Okay, so we talk about something known as the phase angle. This is new. This is a brand new term. Let me show visually what the phase angle is. Here's the phase angle in this case, which is kind of a simplified case. Ready, set, go. This is Greek letter phi equals phase angle. So this is a new introduction. Greek letter phi is the phase angle. And if I go here to this summary diagram, there you see it right here. The phase angle is always defined as the angle between your generator EMF and your generator current. All right, so right here, this is angle phi. Here's an example of angle phi. Over here on the left, here's an example of angle phi. But angle phi, I guess angle phi is the angle between the EMF voltage and current. And you might say, hey, Chris, you said current, but really Isn't it the angle between the EMF voltage and the voltage drop across the resistor? That's saying the same thing. Those are equivalent statements. This phase angle phi is the angle between the EMF voltage right here. This is the EMF voltage and the current. And here's the current right here. And you can see I'm highlighting this current in blue right here. This is my current vector, which is the same as my voltage drop across the resistor. So they really are kind of, well, they're always in phase. All right, so now we have our answer. We have our answer to this problem right here. Okay, what is the phase angle? Let me just say that one more time because I'm talking about part B. What is the phase angle between the circuit current right here and the, I guess I have to add this in. So I'm not quite ready to make this concluding remark. I'm going to get rid of this just to clear the clutter for a bit. All right, so I don't have an inductor, so let me get rid of that. Let's not pretend anymore that doesn't exist, but there for educational background. All right, so I have this voltage drop across my capacitor. So I'm going to do a copy and paste, right? Copy, paste, and do my vector operation. Move this around just to get an accurate visual on this. Okay, so now I can conclude. Here's my net EMF at this point, at this moment in time. At some arbitrary time, this is my EMF right here, I guess. It's a little too thick. Okay, I'll try this. Okay. This is EMF. Okay. EMF. All right. There. All right, so I didn't, let me see, I better fix this a little bit because this is 90 degrees. So from this is 90 degrees because voltage always trails current. Capacitor voltage always trails circuit current by 90 degrees. So that's 90 degrees right there. So this would be 90 degrees. And if VR equals VC, this is the change I have to make. We're talking about the situation when this red vector is the same length as the green vector. So let me make that a little more realistic. The red vector is the same length as the green vector at this particular frequency. So let me just do a few updates here to reflect that. There, this is better. Okay, so what is the angle between the generator EMF, which is right here, and the circuit current, which is right here? It's 45 degrees. It's this angle right here. This is 45 degrees because this must be 45 degrees. So those are the similar angles because if VR equals VC and VR is always perpendicular to VC, that's how I'm getting 45 degrees. Okay. Done with A, done with B. Part C says the angular speed at which the phasors rotate. We have that. We have that. That equals, we have that. So number 7. Six, 7, part D, C, I should say. C is saying omega D equals $. And the good news is it's in number 5. So from number 5, from step number 5 here on my screen, we have omega d equals 2 pi times f equals 2 pi times whatever I have sitting there in memory location A. All right, so what is 2 times pi times alpha A? 679 and some change, radians per second. Radians per second. So if you can provide voltage, if you can provide a source voltage to this circuit at this exact angular frequency, you will have the voltage drop across the resistor right here perfectly match the voltage drop across the capacitor, which is right here at this angular frequency, or similarly at this linear frequency. D says, what's the current amplitude? Okay, so let's finish this number 8. Well, Ohm's law. The answer is Ohm's law, which says V equals IR, but I'm going to isolate R. I equals V over R, and I'm going to personalize this for an AC circuit. So here's the personalization. The current amplitude. So the current amplitude, the maximum current in an AC circuit is going to be whatever that max EMF is. Do I have a number on that? Yep, I do. Over the impedance. So let's just fight the good fight, even though we know what this, well, let's say, so here's the answer. The maximum current attained, the maximum current reached in this circuit at some point in time is going to equal 14.5 volts all over the impedance. And again, the impedance is going to be, I'll sidebar this, R squared plus XL minus XC squared. But XL equals 0. So here's the impedance. Since there is no inductor, it's going to be the square root of R squared. And for me, R is 46 ohms. So square 46 ohms plus XL, which is 0, minus XC. XC, did I calculate? Do we have, where can I? Here's X sub C. Well, here's X sub C minus 1 over omega D times C, all of that squared, because X sub C is in the cellar 1 over omega D times C. So number 10, the maximum current flowing through this circuit is 14.5 volts over the square root of 46 ohms squared. And since I'm squaring it, I can just say, well, it's going to be plus 1 over omega D, which is sitting there in calculator memory location. I guess I'll put this in C. Store alpha C. I'm going to take my angular frequency, the angular frequency of my generator, which is calculator memory location C squared times the capacitance squared, which for me is 32 microfarads, 32 e to the minus 6 squared. And that should do it. There. Right. Let's see. Square root. All right. Let's see. Hmm. And some of you might be saying, Chris, you just wasted some time because I know I know that if my capacitive reactance equals my resistance, which I talked about that, and I know my resistance is 46 ohms. So right away, you could just call this 46 ohms. I kind of saw that just at the last second here. But calculator says 46 squared times 2 reciprocal. Okay. Divided by 14.5. 0.222. $222 milliamps. Okay. That current will produce a voltage drop across the resistor that matches the voltage drop across the capacitor at that moment in time, or at any given moment in time. Okay. Time check. Ooh. I think maybe we'll do, let's see. It's 11:03. Let me do a little bit of a look ahead. Huh. That's pretty time consuming. Okay, we'll do one more problem. One more problem. Quiz 7. Quiz 7 is problem 49. Okay. Last quiz for today. And I think this doesn't take too much time. Chapter 31, quiz 7, skipping skipping some more time-consuming quizzes. We'll get to those probably on Thursday. Okay, so here, let me. We have sort of a fancy looking RLC circuit. There's an RLC circuit, but I have multiple inductors and multiple capacitors. I only have one resistor. In this figure, a generator with an adjustable frequency of oscillation is connected to that resistor and those inductors and those capacitors. What's the resonant frequency? What is the resonant frequency of this circuit, part A? What is the resonant frequency? So number one, well, again, resonant frequency is this special frequency. Resonant frequency happens when the inductor's reactance perfectly blows away, perfectly offsets the capacitive reactance. And from this last problem we did, we showed right here. So I'm just going to take a little copy and paste. We actually did this and said, well, at inductance, at resonance, this is what happens at resonance. Omega D equals 1 over the square root of LC. So this is the, produces resonance. Produces resonance. The most efficient, you're going to get the most current out of your system if it can operate at resonance. All right, so what's the resonant frequency? All right, so number 2 is omega D. Well, let's see. So this is a new statement. For 2 inductors, in series, L equivalent equals, in this case, L1 plus L2. So you add them like resistors. So this is a bit of a new wrinkle. We know how to deal with total inductance. You know for capacitors, for capacitors, for caps in parallel, because those are in parallel, we have CEQ equals C1 plus C2 plus C3. So let's get an equivalent inductance value. L1 plus L2 is going to be 2.37 plus 3.42 millihenry e to the minus 3 Henry. So there's my L value. This is L equivalent. My equivalent capacitor value is going to be 5.4 microfarads plus 3.31 microfarads plus 4.17 microfarads e to the minus 6 farads. So here is the resonant frequency. If I can drive this system at this driving frequency, 1 over the square root of LC, and I guess I'll do 1 over the square root of calculator memory location A times calculator memory location B, because I'm going to put this in A and I'm going to put this in B. So I have a value here that I'll put in calculator memory location C, store alpha C. But that's not what I'm asked to find out. I'm asked to find linear frequency. So omega equals 2 pi f. That means f is going to equal omega over 2 pi, or calculator memory location C divided by 2 pi. 582 and some change. So there's the numerical answer. This is my magical resonant frequency. If I can drive my EMF at this frequency, I will get resonance, which is the happiest place to be. What happens if L1 is increased? So let's just, so for part B, if L1 increases, you know what that means. If L1 increases, LEQ increases. If LEQ, if the equivalent inductance increases, what is that saying about the resonant frequency? So I'm just going to keep my eye right here. This is my resonant frequency right here. If I just increased the what happens to the resonant frequency? Oh, B, if R increases. So sorry for, I looked at C. If R increases. So let me erase this. Sorry. Okay. Try that again. If R increases, so if R increases, what happens to the resonant frequency? Omega D, the driving frequency, the resonant frequency equals no change. No change. Why do I say no change? Because right here, you don't see any dependency on R. R is not here. Resonant frequency only is a function of capacitive reactance and inductive reactance, the capacitor and the inductor, as you can see here. I shouldn't say reactance. Resonant frequency is a function of inductance and capacitance. All right, so that's part B. Part C is saying, what if you increase L1? If L1 increases, you know what that means. The equivalent inductance increases. If the equivalent inductance increases, I'm looking once again at this function right here. And if the equivalent inductance increases, the resonant frequency will decrease. Just looking at number 4, omega D decreases. Just right here. If this L value right here grows, then this shrinks. If the denominator gets big, omega D shrinks. What about D? What if C3 is removed from the circuit? So last but not least, D. If C3 is removed, what happened? My equivalent capacitance, which is right here, if C3 is removed, my equivalent capacitance decreases. If my equivalent capacitance decreases, my driving frequency right here, once again, I'm looking at this situation, or step 4. If my capacitance decreases, that numerator gets smaller. I'm sorry, the denominator gets smaller. If the denominator gets smaller, omega D gets bigger. So, all right. So that's it. That's quite a bit of heavy stuff, but the good news is we have a pretty good timeline. It's now 11:15. Before I sign off, you guys let me know if do you have any requests for extensions on any of these quizzes. If not, then we'll see you on Thursday for a very exciting lab and activity. So like stepbrothers, we'll have some fun activities. All right, see you guys on Thursday. All right.